Welcome to the second semester of Physics for Life Scientists. I'm going to start by saying that there's something really cool about this semester because it is the first semester of physics where the world starts to feel a little bit more magical. So in this semester, we're learning about electricity and magnetism and quantum mechanics. And that world of the very small yields the things in the universe that really puzzled human beings for a very long time and felt like magic and felt like things that, frankly, we had to use, mythology to actually explain. So, for example, electricity and circuits and light, the fact that we can turn on a switch and we're bathed in this illumination. How cool is that? How does that work? Very few of us really understand it, but after the semester, you will. What about magnetism? What about the fact that I can take two magnets and they resist each other, and yet there's nothing in between there? Like, why is there this invisible force that's repelling these two things? Okay, and let's not even get into the quantum mechanics yet. There's all sorts of weirdness there that, quite frankly, layers the world with this almost sense of magic, and that's what I love about it. That's the good news. The bad news is that the world of the really small is, really small. We can't see it. It's hard to develop an intuition for it. Like when we're talking about the world of big things and projectile motion and rotation, these are all things that we've seen before in the real world. It makes it really, really easy to kind of expect what might happen and develop an intuition about it. But in the world of the very small, we don't have such an intuition. So we have to use our imaginations. And that's my first request of this semester, is that you all practice using a little bit of imagination, which can be fun. So, as many of you know, I start every week with a quote of the week, just a little moment of inspiration, a moment to remind us that it is always important to balance our understanding of science with our development as human beings, because they go hand in hand. Because if science develops too far without our spirits developing, I think that can cause trouble in the world, especially in a world where, we have nuclear power and nuclear weapons and many other technologies that seem to be advancing faster than our ethics are. So the quote of the week this week is, "The boundary to what we can accept is the boundary to our freedom." And that's from a meditation teacher named Tara Brach. And so there's a lot of things that we can change in our lives, and there's a lot that we can't. No matter what, we can't change certain things. And those things we could either spend our entire life resisting and pushing up against and causing all this internal tension, or we can learn to accept it and flow with it. It doesn't mean that injustice we should accept, or things that we can actually fight for and change we should accept. But those things in our life that are just life, let's learn to flow with them. And I think that's what this quote is saying. Okay, if you guys will move on to the next slide that says, "Why do we care?" So this first chapter is specifically about the electric force. What is the force that an electron and a proton feel when they are attracted to each other, which we all know happens, right? If you've taken chemistry, you know that electrons and protons are attracted to each other. So as biologists, as doctors who will one day become doctors, and who, as people who do medical research, why do we care, right? Why do we care about electric force? Well, outside of the fact that it is the foundation of all the chemistry that you've ever learned, it is also what holds us together as human beings, right? Our DNA, those strands of DNA, are actually held together with electrical forces. The atoms and molecules that make up our body are held together with electrical forces. Without the electrical force, none of this show exists. Okay, so if that's not important, I don't know what is. If you could go to the next slide, it says that there is something kind of curious about our whole, understanding of electricity, like the layman's understanding of electricity. And that is that it surrounds us completely. We interact with it all the time. We accidentally shock each other. We flick lights on. We plug things in. But we kind of take it for granted. We often forget just how magical it is and how weird it is and how it's kind of amazing that human beings have harnessed that power of electricity to actually make so many things in our life work, like our cell phones, like the computer that you're using to watch this video right now. And so my hope is that after these first few lectures on electricity, you have enough of an understanding that it both solves some of the mystery and adds to it a little bit. Because you'll see that this course leaves a lot of questions because, frankly, there's some things that we still don't understand. And so where does electricity all start? Well, it starts with an atom, specifically the parts that make up an atom. So as you guys know, there is a positive nucleus in an atom. And so we'll take the most basic atom in the world, which is a hydrogen atom. And around that, there is an orbiting electron. And we're going to find out that this picture is actually pretty false. Quantum mechanically speaking, this fellow is not just orbiting. He's actually smeared out all over space around this nucleus. And we don't know precisely where it is. But we'll talk about that more later. The thing to know, though, here is that because there is an electric force that attracts the electron to the proton and vice versa, these orbits are allowed to happen. All right? And we're going to do a whole week on atoms specifically, but the whole property of electricity that you see in the world happens because there is this dynamic between charged particles. Specifically, as you know, electrons and protons are attracted to each other, right? And any like charges are repelled, right? They feel repulsion. All right? And these three little effects here, the fact that there is this electric force between these particles, basically governs all the electric properties that you see in the world. It explains why I will shock my little brother if I touch him on a cold day after scuffing my feet on the carpet. It explains why light moves through a circuit when I turn the light on. And exactly how it does that, that is what this whole course is about. All right? But this is the basics. Because of this, this happens. And because we have atoms, we are able to have electric properties in matter. Okay. One thing that I'd like to clarify is that most folks think that this is about, roughly the size or the scale of an atom. The truth of the matter is, the distance between the nucleus and the electron flying around it is actually massive, much more massive. And there's a video that kind of brings this home that I'm including in the module, so please check it out. But the truth of the matter is, an atom is 99.9999999% empty space. And you're all made of atoms, which means you are all 99.99999% empty space. The whole world, the whole universe that we see is 99.999% empty space, which is wild to think about it because we feel so solid, right? So that's one of the first little pieces of magic that I want to share for this lesson. And one other quick point to make out of this is that many of you heard of neutron stars and black holes and how black holes have such incredible gravity that even light can't escape. The reason why black holes have such a density that they're able to have that kind of gravity is because they're basically just nuclei, right? They're primarily neutrons. And so you have this nuclear density without the electrons in there to create all this extra space. And so consequently, the density is astronomical. And in later chapters, we're going to actually talk about that kind of how much density that is. Like, for example, a teaspoon of just nuclei without the electrons could weigh as much as a mountain range, which is wild. Okay, moving on to every atom is an element on the periodic table. So many of you know this, but the periodic table is organized according to increasing the number of protons in the nucleus. So you start out with hydrogen, which just has one proton, right? And then you add another one, you get helium, and naturally speaking, that'll add another electron as well. But what really defines an element, what really defines the atom, is how many protons are in there. And you have isotopes with different numbers of neutrons, right? You have ions with different number of electrons. But the bottom line is what defines an element, and many of the chemical properties and the mass of that atom is the number of protons. Okay, and so what do you need to do to get to the next element on the periodic table? You just add a proton. Okay, and so with this foundation that it is simply the electric properties of protons and electrons that cause static electricity and all the other electric properties that we see. In the next video, we will talk about how those properties start to manifest in the real world and how, even though they're very small, we can actually see them macroscopically with our eyes.